Hello everyone, today we're discussing Atcoder's beginner contest 393 and we're discussing the third problem of it, the C problem. So the problem statement is written here. So the problem statement revolves around the concept of graphs. So we are given an undirected graph with n vertices and m edges, and every vertex is unnumbered from 1 to n and the edges are numbered from 1 to n. Now, edge I connects the vertices u and v. So it is an undirected graph with u vertices connecting a vertex v. Alright, so it's an undirected graph. Now, we need to make the graph simple by removing some edges. What is the minimum number of edges that must be removed? Right? This is the question. So let's take an example. So we have to remove some edges such that the graph becomes a simple graph. A simple graph means from one vertices there must be an only edge to another vertex. There should not be two edges from vertices or three edges from vertices. All right. So a graph is called simple if it does not contain self loop or multi edges, right? So multi edges is what we call this type of scenario. All right. Okay, like this is the vertices, this is the first vertex, and this is the second vertex. If there are multiple edges between them, then it is called a multi-edge graph. Multi-edge graph. And if a vertex contains a self loop, all right. So if it contains a self loop, then that is a self loop vertex. All right. So there should not be any self loops and there should not be any multi edges. All right. So this is what we need to do. Let's take an example. So let's say this is the graph. So we are given n equal to 3. So we are given three vertices, 1, 2, and 3. All right. And we are given five edges, right? So we are given five edges. The first edge is from 1 to 2. All right. So 1 and 2 are connected. 1 and 2 are connected, right? 1 and 2 are connected. Then 2 and 3 are connected. So 2 and 3 are connected. Then 3 and 2 are connected. Now look closely. 3 and 2 are connected. So this means 3 and 2 are connected. Now 3 and 1 are connected. So 3 and 1 are connected. And 1 and 1 are connected. So it is a self loop, right? So the graph is something like this. So how many edges do we need to remove? So first of all, we need to remove this edge because this is a self loop, right? So we need to remove the self loop edge, right? So this should be removed. And we also must remove this edge, right? This one, right? Because this is a multi edge, right? So multi edge must be removed. So the solution for this type of questions lies in a very simple manner. So a very optimal or very brute force solution would be we will not make an undirected graph. Okay, first of all, we will not make an undirected graph. We will make a directed graph. What do you mean by directed graph? So let's say this was the example, right? So in this case, we were given 3 and 2. All right. So if you look closely, we are given 2 and 3 and then 3 and 2, right? So I will just make an edge from 2 to 3. All right. So I will just make an edge from 2 to 3. And when 3 and 2 comes, right? So I will also make an edge from 3 to 2. Now for 2, for index number 2, for vertex number 2, I will check for all its children. For all its children. I will check for all its children. Who are the children of 2, right? 2 is only connected to 3, right? So the children of 2 are 3. So I will check for all its children if 2 is present or not. All right, very simple approach. See, I have just made an edge from 2 to 3. All right. Now I will check for all children of 2, right? So the only child of 2 is 3, right? So I will check for 3 and I will check if 3 is connected to 2. That means there is a multi edge here. Can I say it like this? So what I will do is I will make an adjacency list. All right. So I will make an adjacency list. Now from the question, as you can see, what do we find? One is connected to 2 and one is connected to 1. All right. So for 1, the adjacency list would look like this. 1 is connected to 1 and 1 is connected to 2. All right. So this is the adjacency list. Next, 2 is connected to 3 and that's it, right? So 2 is only connected to 3. So 2 is only connected to 3. And 3 is connected to whom? So 3 is connected to, I think so, 1 and 3 is connected to 2 and 3 is connected to 1. All right. So 3 is connected to 1 and 2. Now, for every edge, I will check is it containing the same number as itself? All right, so let's do the C++ code for this. So first we are given n and m, so I will just input n and m, c and m. Then I am given m vertices. So if you look closely, I am given m vertices. So I will traverse for m times. So I will traverse for m times, and I am given two vertices u and v. All right, so I will just input u and v. Now I need to make an adjacency list. All right, so I will make an adjacency list. So unordered map of LL, and I instead of using vector LL, So instead of making a vector adjacency list, I will make a set adjacency list. All right. So this is how we normally make an adjacency list, but instead of using a vector, I will use an unordered set. What will I use? An unordered set, because I don't want multiple edges, right? So I will just use an unordered set here. All right. Now what will I do? I will adjacency of u will insert v, right? This is what we'll do, right? But at first I have to check if adjacency of u already contains v, right? So adjacency of u dot find v. That means there is a self loop here, right? So there must be an multi-edge here, multi-edge here. So what will I do? I will just increase my count variable. Simple. So I'll just increase my count variable. Let's make a count variable first. So count is initially 0, right? So I will just increase a count variable, right? Let's say there was 1 to 2 and there was again 1 to 2 somewhere here, right? So if you take a look at this example, as you can see, there is 5 1, right? There is 5 1 and there is a 5 1, right? So in this case, there is 2 edges, right? So there is a multi-edge here, so I'll just increase my count variable, right? So actually it is not a multi-edge, same u and v again. So in that case, I will just increase my count variable. Now what am I doing? I'm traversing for every vertices, right? So I'm traversing for every vertices. I'll just check if adjacency of I dot contains I, right? So if self loop is present, is not equal to adjacency of I dot end. So that means there is a self loop here, right? So self loop, so I'll just increase my count variable. Now what will I do? I'll traverse for every neighbor of I, right? So I'll traverse in every neighbor of adjacency dot I, right? So I'll traverse in every neighbor, and what will I do? If adjacency of neighbor contains I, right? So if adjacency dot neighbor contains I not equal to, then that means there is already an edge from u and v, and there is also an edge from v to u. That means there is a multi-edge here, right? So there is a multi-edge here. So I'll just increase my count variable, and simultaneously, what will I do is I'll just erase it from it, right? So I'll just erase I from the variable, and you can also erase this from So adjacency of I dot erase I, right? So you can also erase the edge, erasing self loop, right? So I'll just erase the self loop, and what I'm doing is I'm erasing the multi-edge. All right, that is what we're doing. And finally, what we're doing is we will just print the count variable. So that's it, simple as that. Let's run this. All right, so as you can see, all the test case got submitted. Now let's submit this approach. So let's submit this one. Yeah, so as you can see, the solution got accepted. Right, so let's do the Java code for the same. So in the Java code, first we're inputting n and m. So n is the number of vertices, and as m is the number of edges. So number of vertices and then edges. All right, so we're inputting n and m, and then what we are doing is we will traverse for m times, right? The number of edges times I plus plus. And every time we are inputting 2 edges, right? So there is a direct edge connecting u and v, right? So first I will input u, and then I will input v, right? So I'll just input u and v. Now in the adjacency list, right? How do we make an adjacency list in Java? So I'll just use a hash map here. So I'll make an hash map of integer, comma. Normally what we do is we make an integer hash map, right? So this is the adjacency list, right? But instead of using an array list, what I will do is I'll use an unordered set, right? So I'll use a hash set here, right? So I'll make an hash set integer. The reason for using a hash set is because there must be only one edge from u to v, right? So there should not be multiple edges. So I'll just use a hash set. You can also use an array list here. The array list and hash sets functions are the same for adding and removing. So you can also use an array list here. So what I'll do is if adjacency list not contains key, so I'll just put an u here, right? So put if absent, you can also use it like this. So instead of using adjacency list, put if absent. So I'll just put u if new hash set this one, right? So if u is not present in the hash set, then I'll just put here, right? But first I need to check if there are same edges here, right? So if you look at this example, there is an edge connecting 5 and 1, and there is also an edge connecting 5 and 1. So 5 and 1 are appearing 2 times, right? So I just have to check if mp dot contains key u, right? So if mp dot already contains key u, and mp.getU contains v. So if already u contains v, all right, so that means the edge is coming for a second time. The edge is coming for a second time. That means there is a again edge, right? So the edge is coming for a second time. So I'll just increase my count variable here. So let's just make a count variable. So count is initially set to 0. Right? So if the adjacency list, not MP, the adjacency list already contains U and V. So adjacency list already contains an edge from U and V, edge of U to V, right? So I'll just increase my count variable. And then what I'll do is I'll get U and I'll just add V to it. All right. So I'm adding an edge to it. So that's it. That done. Now what are we doing? I'm traversing for every edge. As you discussed in the approach, I'm traversing for every edge. First, I will check for self loop and then I'll check for multi edges, right? So I'll just write it down. So how do you check for self loop, right? So first of all, we just need to check if adjacency list should contain the ith key, right? So the ith key must be present in the adjacency list. Then only we can check for self loop and multi edge, right? So first of all, we'll check for self loop. So if adjacency list, sorry, adjacency list dot get I, if it already contains I, right? So if it already contains I, that means there is a self loop. So I'll just increase my count variable, right? So what I'll do is I'll just increase my count variable. And what you can also do is you can just remove the self loop, right? So if you want to remove it, so I'll just remove it from the self loop. So I'll just removing the self loop. Right? So I'll just remove the self loop from it. Now I have to check for multi edges. So what I will do is I will traverse for all neighbors of the current node. So I will traverse in neighbor of adjacency list.getI. So I'm traversing for all the neighbors and I'm checking if adjacency list.contains key neighbor and the neighbor already contains I, right? So that means there is a multi edge here, right? So multi edge is present here. Multi edge is present here, present. So I'll just increase my count variable, and you can also what you can also do is uh, you can just remove the multi edge, right? So remove I, right? So that is what you can do, right? So you can just remove the multi edge. So removing the multi edge, and finally what we'll do is we'll just print the count variable. So I'll just print the count variable here. So let's run this code. So let's try and check this. All right, so as you can see, all the test case got submitted. Now let's submit this code. It is taking some time. Let it judge. Let's hope it does not give it is giving a TLE. All right, so we have to check for TLE. All right, so let's review our code very fast. Now, what I'm doing is I'll just, okay, count variable. If it contains I, all right, okay, okay. So we can do just you can just use this one. Na, instead of checking a self loop here, we can just use this one, right? So if neighbor equal to I, right? So that means there is a self loop here, right? Self loop here, right? So what I'll do is I'll just increase my count variable here, right? So what I'll do is there is a self loop present now. So I'll just increase my count variable. You can also do it like this, right? So this is for checking the multi edge, right? This was checking the self loop, and this is for checking the multi edge, right? Let's run this. The previous approach was giving TLE, but the test case were getting submitted. All right, so it is giving a modification error. All right. It is giving some kind of error. So let's check. We must remove the self loop, right? So I'll just removing the self loop. Now let's run this. All right. So else, else we will check for the multi-edge, right? So let's do this kind of code. All right. So if the self loop is not present, then there must be a multi-edge here. So let's try this. All right. It is still giving some kind of error. All right. So let's reverse the code. Let's see what was the problem in the original code. So I'm just reversing all of this. Let's see. Okay. Let's run this part. If there is a self loop, then I'll just remove it. and then for every neighbor I'm checking for the same. Do I need to use long here, right? So let's make every integer into long. All right, so I'll just make every integer into long. All right, and here in long I use the next long. All right, so let's do this. Then in case of an integer, I'm just converting everything into long. All right, so I'm just converting every into long. All right, so long and print ln. All right, so let's run this part. I'm just converting everything into long. Let's hope so it gets submitted. I don't think so. There might be a problem in getting submitted, but for some reason it is giving some kind of error. Yeah, so as you can see, the long solution got submitted. Now I'll explain the approach once again. So what we did was, let's say there was an edge from 1 to 2. All right, so I'll just make a directed edge here, and I'll check for every neighbor of 1. So I'm checking every neighbor of 1. So the only neighbor of 1 is 2. So I'll check, is 1 present in 2? Is 1 present? Neighbor of 2 is 1 neighbor of 2. So I'll check if is an edge from 2 to 1 here, right? So if there is an edge from 2 to 1, that means there is a multi-edge here, right? So I'm just checking for multi-edge here. So if there is a multi-edge, then I'll just remove this. So I'll just increase my count variable and I'll just remove that multi-edge, all right? And in case of a self loop, I'll just check if adjacency list dot get I, if it already contains I, right? So adjacency dot get I dot already contains I. So that means there is a self loop here, right? Right. In Java, you can write it like this, and in C++, you can write it like this, right? So adjacency list I dot find I, right? So if I is already present in the ith node, that means there is a self loop, right? So in that case, I'll just increase my count variable. Simple. All right. So the time complexity of this approach is O of n, and the space complexity of this approach is O of n. All right. And in some cases, it might be O of n log n. In case of using a map and a set, the time complexity may rise to O of n log n. And if you look at the constraints very well, the constraints is n is 10 raised to 5 and m is 10 raised to 5. So a complexity of O of n or O of n log n will get accepted. All right. So I'll see you in the next video. Till then, keep learning. Take care. Bye bye.